For most of modern history, humanity believed it had finally reached a quiet understanding with the universe, a sense that while the cosmos was vast and mysterious, its basic story had been mapped, organized, and largely settled into something we could explain with confidence. The Big Bang gave us a beginning, inflation gave us expansion, gravity gave us structure, and time gave us order, and together these ideas formed a narrative that felt complete enough to rest on. Galaxies were supposed to form slowly, patiently assembling themselves from clouds of gas and dark matter over hundreds of millions of years, growing from small, chaotic fragments into the elegant spirals and massive structures we see today. Stars were expected to ignite gradually, one generation after another, enriching the universe step by step, never rushing ahead of the cosmic clock. In this story, nothing important happened too early, and nothing arrived before its time. For decades, astronomers refined this picture, adjusting numbers, improving measurements, and debating details, but rarely questioning the foundation itself. The universe, it seemed, followed the rules we had uncovered, and while there were mysteries left to solve, they existed comfortably within a framework that felt stable and reassuring. This confidence was not arrogance, but familiarity, the quiet belief that the universe, while large, played fair, revealing its secrets slowly and logically to those patient enough to look. Telescopes like Hubble reinforced this feeling, showing us distant galaxies that fit neatly into expectations, younger, smaller, dimmer, exactly where theory said they should be. Each new observation felt like confirmation, rather than confrontation, strengthening the idea that we were reading the universe correctly. Over time, this sense of understanding settled into textbooks, lectures, documentaries, and public imagination, shaping how we taught the story of everything from the first moments after the Big Bang to the rise of galaxies like our own Milky Way. It became easy to forget that this story was built not from certainty, but from the limits of what we could see. Because every telescope, no matter how powerful, is also a boundary, defining not only what we observe, but what we assume lies beyond our reach. And as long as those boundaries remained fixed, the story remained comfortable. Yet science has a quiet habit of becoming most dangerous when it feels most complete, because confidence can mask the presence of unanswered questions waiting just beyond the edge of perception. For all our equations and simulations, the universe itself never promised to behave in ways that feel intuitive or orderly to the human mind. It simply does what it does, indifferent to whether our models survive the encounter. The history of science is filled with moments where a single observation shattered centuries of certainty, not because scientists were careless, but because reality turned out to be stranger than expectation. Earth was once believed to sit at the center of everything. Time was once thought to flow the same everywhere. And space itself was once considered an empty stage, rather than something that could bend and stretch. Each time, the universe waited patiently for us to look more closely. By the early 21st century, cosmology once again felt settled. Not perfect, but reliable. Like a map with a few missing details, rather than an entirely wrong direction. Few suspected that one of the most basic assumptions, the pace at which the universe builds structure, was about to be challenged. Fewer still imagined that the challenge would come not from speculation or philosophy, but from light that had been traveling for more than 13 billion years, carrying a message written long before Earth existed. The idea that something fundamental might be wrong with our timeline was not a fear anyone actively held, because timelines feel objective, anchored by numbers and measurements that appear immune to doubt. Yet those numbers rely on interpretation, and interpretation relies on observation, and observation depends entirely on how deeply we can look into the darkness. The universe has always hidden its earliest chapters behind distance, using space itself as a veil that only the most sensitive instruments could ever hope to lift. For a long time, we believed that when we finally pierced that veil, we would simply see confirmation of what we already believed. Younger galaxies behaving exactly as predicted, small and primitive, waiting patiently to grow. What no one was fully prepared for was the possibility that the universe, when seen clearly for the first time, would not match the story we told ourselves about its youth. And that possibility remained dormant, almost invisible, until humanity built a telescope capable of seeing not just farther, but earlier, reaching so deep into space that distance itself would become a form of time travel. Because to understand why this discovery matters, and why it breaks so much of what we thought we knew, we must first understand a simple but unsettling truth: that every step outward into the cosmos is also a step backward into the past. And the deeper we look, the closer we come to witnessing the universe as it truly was at the very beginning, which is where the next chapter of this story must begin. To understand why the discovery of an impossibly old galaxy is so unsettling, we must first understand a concept that sounds simple on the surface, but quietly reshapes everything we know about reality, which is that distance in the universe is inseparable from time itself. When we look at the night sky, our instincts tell us we are seeing the universe as it exists right now, frozen in a single moment. But this is an illusion created by the limits of human perception. Light does not arrive instantly, it travels, and it travels at a finite speed, meaning every photon that reaches our eyes carries a history with it. The moon appears as it was a little over 1 second ago, the sun appears as it was 8 minutes ago, nearby stars appear as they were years or decades ago, and distant galaxies appear as they were billions of years in the past. The farther away an object is, the longer its light has been traveling, and the older the version of the universe we are witnessing. This means that telescopes are not merely instruments for seeing faraway places, but machines for looking backward through cosmic history. Every increase in observational power is also an increase in how deeply we can peer into time itself. This idea feels abstract until it is fully absorbed, because it means there is no such thing as seeing the universe as it is now in its entirety, only fragments of different eras layered together in our field of view. The sky is a collage of time, a patchwork of moments spread across billions of years, stitched together by light arriving simultaneously from vastly different distances. When astronomers talk about looking deeper into space, they are really talking about approaching the beginning of everything, inching closer to the moment when the universe first began to assemble structure out of chaos. For decades, this backward journey was limited by technology, because even the most powerful telescopes could only collect faint, stretched light from the distant past. As the universe expands, the light traveling through it is stretched along with space itself, shifting from visible wavelengths into infrared, becoming weaker and harder to detect. This redshifting acts like a natural curtain, hiding the earliest galaxies from ordinary sight and placing them just beyond the reach of traditional instruments. Hubble could see far, but not far enough to truly glimpse the universe's infancy, leaving a gap between theory and observation that scientists filled with models, simulations, and educated expectations. Within those models, the early universe was a dark and violent place, filled with raw material but lacking the complexity seen later. The first stars were thought to be massive, short-lived, and rare, igniting pockets of light in an otherwise dim cosmic landscape. Galaxies, in this picture, formed slowly as gravity pulled matter together over long periods of time, assembling structure piece by piece. The earliest galaxies were expected to be small, chaotic, and fragile, barely holding themselves together against the expanding universe. This framework became so familiar that it felt inevitable, as though the universe could not have unfolded any other way. But all of this confidence rested on an assumption, which was that when we finally looked far enough back, the universe would politely match our expectations. The problem with assumptions is that they remain invisible until they fail. Every improvement in telescope technology is a test of humility, because it asks whether reality agrees with the stories we have told ourselves. When a new telescope extends our vision, it does not merely add detail, it exposes whether our mental picture of the cosmos survives contact with actual light from the past. The deeper we look, the more dangerous that question becomes. At extreme distances, the universe is younger, denser, hotter, and less forgiving of tidy explanations. Time itself behaves differently, because early cosmic eras unfolded rapidly, with enormous changes occurring in what we would now consider impossibly short spans. A few 100 million years after the Big Bang may sound like plenty of time from a human perspective, but on cosmic scales it is a blink, barely enough for gravity to sculpt matter into anything complex. This is why the concept of cosmic time matters so deeply to astronomers, because it sets strict limits on what should be possible at each stage of the universe's development. If something appears too early, it is not just surprising, it is destabilizing. because it implies either that our understanding of time, matter, or both is incomplete. Light carries with it not only images, but timestamps, and those timestamps are what allow scientists to build a chronology of cosmic events. When those timestamps align with theory, confidence grows, but when they do not, uncertainty spreads outward through every related assumption. This is why the act of looking deeper is never neutral, because it always carries the risk of revealing something that does not belong. As astronomers prepared to use a new generation of telescopes capable of seeing the faint infrared glow of the earliest galaxies, they expected refinement, not revolution. They expected to fill in missing details, not rewrite the opening chapters of cosmic history. The language used in proposals and predictions was cautious, measured, confident that while surprises might occur, they would fit within existing frameworks. Few openly anticipated that the universe might reveal structures that appeared fully formed far earlier than theory allowed. Yet the universe has never been obligated to respect our expectations. When light has traveled for more than 13 billion years to reach us, it does not care what models predicted it should look like. It simply arrives, carrying information from a time when the cosmos was young and unfamiliar, asking us whether we are willing to accept what it shows. And as the next chapter will reveal, when the James Webb Space Telescope finally opened this deepest window into the past, the universe did not behave politely at all, because what scientists expected to find, and what Webb actually saw, would soon diverge in ways that no one could comfortably ignore. Before the James Webb Space Telescope ever opened its golden mirror to the darkness, scientists believed they had a clear and reasonable picture of what the early universe should look like. Not because they had seen it directly, but because the laws of physics seemed to leave little room for alternatives. In the aftermath of the Big Bang, the universe was hot, dense, and nearly uniform. A rapidly expanding sea of particles with only tiny fluctuations in density. Over time, gravity was expected to amplify those small irregularities, slowly pulling matter together into clumps that would eventually become stars and galaxies. This process, according to prevailing models, was gradual and inefficient, especially in the universe's earliest stages. The first few 100 million years were thought to be a cosmic dark age, a period where matter existed mostly as diffuse gas, with light rare and fleeting. The earliest stars, known as population 3 stars, were expected to be massive, unstable, and short-lived, burning brightly for only a few million years before exploding and enriching their surroundings with heavier elements. These early stars were not supposed to form elegant galaxies, but rather loose, chaotic groupings that barely resembled the grand structures we see today. Galaxies themselves were expected to assemble hierarchically, starting small and growing larger through countless mergers and slow accretion of material. In this framework, large, well-organized galaxies required time not just to accumulate mass, but to settle into stable configurations. Spiral arms, dense cores, and significant stellar populations were thought to be hallmarks of maturity, the result of billions of years of evolution rather than something that could appear suddenly. Astronomers predicted that when we finally observed galaxies from the universe's first few 100 million years, they would appear faint, irregular, and underdeveloped, barely visible even to the most powerful instruments. These expectations were not arbitrary, because they were grounded in simulations that incorporated gravity, gas dynamics, radiation, and dark matter, all tuned to match what we observed in the nearby universe. When these simulations were run forward from the conditions of the early universe, they consistently produced a slow, step-by-step buildup of structure. Nothing in the equations suggested that massive galaxies could form quickly without violating fundamental constraints. Dark matter halos, which provide the gravitational scaffolding for galaxies, were expected to grow over time, merging and deepening gradually. Gas, meanwhile, needed time to cool, collapse, and form stars, a process limited by physics that could not simply be rushed. Even under optimistic assumptions, early galaxies should have been small and dim, with limited star formation and low heavy element content. This understanding shaped decades of astronomical thinking, influencing how scientists interpreted every distant observation. When Hubble glimpsed galaxies at high redshift, their faintness and irregular shapes seemed to confirm this picture, reinforcing confidence that the early universe was behaving as expected. Each new observation fit neatly into the timeline, adding detail but rarely challenging the underlying structure. The idea that the universe followed a predictable developmental path became deeply ingrained, not just in academic circles, but in how cosmology was communicated to the public. The early universe was portrayed as a slow awakening, a gradual lighting of the cosmic stage rather than a sudden burst of complexity. This narrative was comforting, because it suggested that complexity required patience, that the universe, like life itself, unfolded at a measured pace. It also implied that by understanding the rules governing that pace, we could extrapolate backward with confidence, reconstructing the universe's earliest moments from the structures we see today. Few questioned whether those rules might behave differently under the extreme conditions of the early cosmos. After all, the equations were well tested, the simulations robust, and the observations consistent. The possibility that the universe might have found shortcuts, accelerating structure formation in ways we did not anticipate, seemed remote. To propose such an idea would have required evidence strong enough to outweigh decades of accumulated confidence. As a result, expectations going into the James Webb mission were cautiously optimistic but fundamentally conservative. Webb was expected to push boundaries, to reveal fainter and more distant galaxies, and to fill in missing pieces of the early timeline, but not to overturn it. Scientists anticipated surprises, but surprises that could be accommodated with minor adjustments, not revelations that would force a rethinking of cosmic history. The language used in predictions reflected this mindset, emphasizing refinement rather than disruption. No one openly planned for the possibility that Webb might detect galaxies that appeared fully formed at a time when the universe was supposed to be barely out of its infancy. Such a finding would not just be unexpected, it would be deeply problematic, because it would suggest that either galaxies formed far faster than allowed by current physics, or that our understanding of the early universe was missing something fundamental. This is why the expectations surrounding Webb matter so much, because they set the stage for what would follow. When a telescope looks where no telescope has looked before, it does so carrying the weight of theory, prediction, and assumption. The universe is then given a chance to agree or disagree. And as the next chapter will show, when Webb finally began sending back its first deep images, the universe did not merely tweak the existing picture, but began to hint, quietly at first, that the early cosmos was far more advanced than anyone had prepared for, forcing scientists to confront the uncomfortable possibility that their expectations had been too small for the reality waiting in the dark. The arrival of the James Webb Space Telescope marked a quiet but profound turning point in humanity's attempt to understand the universe, not because it promised spectacle, but because it promised access to a realm of cosmic history that had remained unreachable until now. Unlike its predecessors, Webb was designed not to see the universe as it appears to the human eye, but as it truly is at extreme distances, where light has been stretched, weakened, and transformed by billions of years of cosmic expansion. As the universe expands, the light traveling through it is elongated, shifting from visible wavelengths into infrared, meaning that the oldest and most distant galaxies are effectively invisible to traditional optical telescopes. Hubble, despite its revolutionary achievements, was constrained by this limitation, able to glimpse only the brighter, more evolved structures of the early universe, while the faintest and most ancient light slipped past unnoticed. Webb was built specifically to catch that escaping light, to see what had always been there but could not be observed, and in doing so, to test the assumptions that had filled the observational gap for decades. Its massive gold-coated mirror was engineered to collect faint infrared photons with unprecedented sensitivity, while its instruments were cooled to near absolute zero to eliminate interference from its own heat. This allowed Webb to operate not as a general-purpose telescope, but as a precision instrument tuned to the whispers of the early cosmos. When Webb unfolded in space and aligned its mirrors, the anticipation within the scientific community was intense but measured, because while everyone expected remarkable images, few openly predicted that those images would challenge foundational ideas. The first deep-field observations were planned carefully, targeting regions of the sky that appeared empty to previous telescopes, places chosen precisely because they offered a clear window into the distant past. These were not dramatic regions filled with nearby galaxies or brilliant stars. but dark patches of sky where faint, ancient light had the best chance of standing out. When Webb began collecting data from these regions, it did not deliver its revelations with sudden clarity, but with subtlety, through patterns that only became apparent as images were analyzed and reanalyzed. At first glance, the images were stunning but familiar. A dense field of galaxies stretching across space and time, each one a point of light carrying an ancient story. But as scientists began measuring distances, brightness, and structure, a sense of unease slowly emerged. Some galaxies appeared brighter than expected for their estimated age, shining with an intensity that suggested a surprising amount of mass and star formation. Others showed signs of organization that should not yet exist, shapes that hinted at stability rather than chaos. These were not isolated anomalies, but recurring patterns appearing across different observations, persistent enough to demand attention. Webb was not just seeing farther than Hubble, it was seeing differently, revealing a universe that seemed to have matured faster than theory allowed. The telescope's ability to detect infrared light meant it was capturing galaxies from a time when the universe was only a few 100 million years old, an era previously represented mostly by speculation and simulation. In that era, according to established models, galaxies should have been tentative and incomplete, struggling to assemble under the competing forces of gravity and expansion. Yet Webb's data suggested that something else had happened, that the early universe may have been far more efficient at building structure than anyone had anticipated. The significance of this possibility did not lie in any single image, but in the accumulation of evidence that refused to align neatly with expectations. Astronomers are trained to be skeptical of early interpretations, especially when new instruments are involved, because calibration issues, data processing errors, and selection effects can all produce misleading results. Every unusual finding was scrutinized, cross-checked, and debated, with teams around the world working independently to verify measurements and rule out simpler explanations. Despite this caution, the pattern remained: galaxies appearing too bright, too massive, and too organized for their place on the cosmic timeline. This was the moment when Webb ceased to be just a more powerful telescope and became a challenge to long-held assumptions. The early universe, once thought to be slow and tentative, was beginning to look surprisingly confident, as if it had found ways to assemble complexity far earlier than expected. The discomfort this created was subtle, but profound, because it struck at the heart of how scientists reconstruct cosmic history. If galaxies formed faster, then the role of dark matter, gas cooling, and star formation efficiency might need to be reconsidered. If star formation was more intense in the early universe, then the conditions under which the first stars ignited might be very different from what models assumed. Each possibility opened the door to further questions, not just about galaxies, but about the fundamental processes that shaped everything that followed. Webb's observations did not yet provide answers, only tension, a growing sense that the early universe was not behaving according to the script. The telescope had done exactly what it was designed to do, which was to look where we had never looked before and report what it found without regard for our expectations. In doing so, it exposed the fragility of confidence built on incomplete observation. The universe had not changed, but our access to it had, and that access was revealing a past that felt uncomfortably advanced. As the data continued to arrive, scientists realized that they were no longer simply filling in missing details, but confronting the possibility that the opening chapters of cosmic history might need to be rewritten. And it was within this growing unease, amid careful measurements and cautious language, that a particular observation began to stand out, one galaxy whose apparent age and maturity pushed the tension beyond discomfort and into outright contradiction, setting the stage for the moment when curiosity would turn into astonishment in the next chapter. The first signs that something was deeply wrong did not arrive as a dramatic announcement or a single shocking image, but as a quiet accumulation of details that refused to stay in their expected places, because science rarely collapses all at once, and instead unravels slowly, thread by thread. As astronomers began examining Webb's early deep field data, they noticed galaxies whose brightness immediately felt uncomfortable, objects shining far more intensely than models predicted for their apparent distance and age. Brightness in astronomy is not merely aesthetic, because it carries information about mass, star formation rate, and the total amount of material locked inside a galaxy, and these early measurements suggested that some galaxies contained far more stars than should have been possible so soon after the Big Bang. At first, this discrepancy was easy to dismiss, because early data is notoriously deceptive, and new instruments often reveal quirks that vanish once calibration improves. Scientists questioned whether these galaxies only appeared bright because of dust effects, gravitational lensing, or subtle measurement errors that could inflate their apparent size and luminosity. Each of these possibilities was reasonable, and each offered a way to preserve the existing cosmic timeline without invoking anything radical. But as more data arrived, the pattern refused to fade. Across different regions of the sky, across different observing programs, the same unsettling trend appeared again and again. Galaxies that looked far too mature for their age, as if the universe had skipped several steps in its own development. Some of these galaxies exhibited smooth, compact structures, rather than the messy, fragmented shapes expected from early cosmic chaos, suggesting that their stars were not just present, but organized. Organization implies time, because chaotic systems require long periods to settle into stable configurations, yet these galaxies were appearing at epochs when the universe was supposed to be barely learning how to build anything at all. Spectroscopic measurements deepened the unease, because they allowed astronomers to estimate how quickly stars were forming within these galaxies, and the inferred rates were astonishingly high. Star formation on this scale requires vast reservoirs of cold gas and efficient cooling mechanisms, processes that were thought to be limited in the early universe by intense radiation and turbulent conditions. According to established models, early star formation should have been sporadic and inefficient, struggling against feedback from the first massive stars that would heat and disrupt surrounding gas. Yet Webb's observations suggested that some early galaxies were converting gas into stars at a pace that rivaled or exceeded that of much later cosmic eras. This raised a troubling question, which was not just how these galaxies formed, but how they managed to sustain such activity without tearing themselves apart. The more scientists examined these early signals, the more they felt like messages arriving out of sequence, as though the universe had sent back pages from a later chapter and inserted them near the beginning of the book. The discomfort spread beyond brightness and star formation into estimates of mass, because mass in galaxies is closely tied to dark matter halos, the invisible scaffolds that provide the gravitational pull needed to hold galaxies together. Dark matter halos were expected to grow gradually, merging and deepening over time, but the apparent mass of these early galaxies implied halos that had assembled with startling speed. This challenged assumptions about how quickly dark matter could clump in the early universe, a process thought to be constrained by initial density fluctuations left over from the Big Bang. If dark matter halos were forming faster than expected, then the entire sequence of structure formation might need revision. Alternatively, if the halos were not unusually massive, then the stars themselves must have formed with unprecedented efficiency, raising questions about the physics governing gas cooling and collapse under primordial conditions. Neither option was comfortable, because both implied gaps in our understanding of fundamental processes. As discussions unfolded in papers, conferences, and informal conversations, a subtle shift occurred in tone, moving from curiosity to concern. Scientists are trained to expect anomalies, but they are also trained to recognize when anomalies begin to cluster into something more significant. What made these early Webb findings so unsettling was not that they were strange, but that they were consistently strange in the same direction, always hinting at a universe that was doing too much too soon. Each new observation added weight to the growing suspicion that these were not isolated outliers, but glimpses of a broader pattern. At the same time, caution remained paramount, because extraordinary claims demand extraordinary evidence, and no one wanted to overinterpret data from a telescope still in its early operational phase. Teams worked diligently to refine redshift measurements, ensuring that these galaxies truly belonged to the early universe and were not closer interlopers masquerading as ancient objects. They tested models that accounted for dust obscuration, explored alternative explanations involving exotic stellar populations, and re-examined assumptions about how light travels through expanding space. Yet even as these efforts narrowed uncertainties, the core tension persisted. The galaxies still looked too big, too bright, and too organized to fit comfortably within the accepted timeline. This tension began to spill beyond the specifics of individual galaxies and into broader reflections on cosmology itself. Because if early galaxies were more developed than expected, then the conditions of the early universe might have been very different from what models assumed. Perhaps gas cooled more efficiently, or perhaps the first stars formed in ways that enhanced subsequent star formation rather than suppressing it. Perhaps dark matter behaved differently at early times, or perhaps feedback processes were less disruptive than thought. Each hypothesis carried implications that rippled outward, touching everything from the reionization of the universe to the chemical enrichment of intergalactic space. What had begun as an observational curiosity was slowly becoming a conceptual challenge. And within this growing unease, amid a field of unexpectedly mature galaxies, one object began to draw particular attention. A single galaxy whose apparent age and structure pushed the problem beyond discomfort and into outright contradiction, because if its measurements were correct, it existed at a time when galaxies like it simply should not have existed at all, leading directly into the moment when scientists would confront the galaxy that should not be there in the next chapter. The moment this particular galaxy entered the conversation, the tone of scientific discussion changed, because this was no longer a subtle statistical trend or a cluster of mildly uncomfortable data points, but a single object whose existence challenged the very sequence of events that underpins modern cosmology. This galaxy did not announce itself with drama, but with defiance, quietly appearing in Webb's observations at a redshift so high that it placed the object astonishingly close to the beginning of cosmic time. Based on the light reaching Webb's instruments, the galaxy appeared to exist when the universe was only a few 100 million years old, a time when matter was supposed to be sparse, structures small, and complexity rare. Yet the galaxy's brightness suggested a mass that rivaled or exceeded that of galaxies thought to take billions of years to assemble. Its light carried the signature of a substantial population of stars, not just a handful of early pioneers, but a dense and coherent system that had already undergone significant formation and organization. In practical terms, this meant the galaxy looked less like a fragile newborn and more like a fully formed adolescent, appearing far too early in the cosmic timeline to make sense. When astronomers attempted to reconcile this with existing models, the numbers refused to cooperate, because to reach such mass and luminosity in so little time would require star formation rates that bordered on the absurd. The galaxy would have needed to convert gas into stars with near-perfect efficiency, sustaining that process without interruption, and doing so in an environment thought to be hostile to stability. Even under extreme assumptions, the timescales did not align, because gravity alone could not pull matter together fast enough without violating constraints imposed by the expansion of space itself. This was not merely a matter of stretching parameters, but of confronting limits that had long been considered fundamental. The galaxy's apparent maturity also raised questions about its internal structure, because organized stellar populations imply not just formation, but regulation, feedback, and balance, processes that normally require long periods of trial and error. Early stars were expected to be violent, blasting surrounding gas with radiation and winds that would suppress further star formation, yet this galaxy seemed to have overcome or avoided such disruption. Its light hinted at metals heavier than hydrogen and helium, elements forged in earlier generations of stars, implying that star formation had begun even earlier than the galaxy's observed age suggested. This pushed the problem back further in time, forcing astronomers to consider the possibility that the universe had begun forming stars almost immediately after the cosmic dark ages ended. The implications cascaded outward, because if this galaxy existed so early, then it was unlikely to be alone, and its presence hinted at a broader population of similarly advanced systems lurking just beyond the edge of detection. The discomfort was not just scientific, but philosophical, because the discovery challenged the narrative of gradual emergence that had shaped our understanding of cosmic history. It suggested that the universe may have been capable of assembling complexity with startling speed, as though it were primed to build structure rather than struggling against entropy. This galaxy did not fit into the existing timeline as a minor exception, but as a contradiction, a sentence that refused to belong in the paragraph where it appeared. Scientists responded with caution rather than excitement, because when data threatens to upend foundational assumptions, the instinct is to question the data before questioning the framework. Teams scrutinized every step of the measurement process, from redshift estimation to brightness calibration, searching for errors that could rescue the established story. They considered whether dust could be amplifying the galaxy's apparent luminosity, whether gravitational lensing might be magnifying its light, or whether unusual stellar populations could be skewing interpretations of mass and age. Each potential explanation was examined carefully, and while some could soften the tension slightly, none could eliminate it entirely. The galaxy remained stubbornly out of place, refusing to retreat into the margins of uncertainty. Its existence forced a deeper confrontation with the assumptions embedded in cosmological models, because if even one such object truly existed, then the universe had found a way to accelerate structure formation beyond what theory allowed. This raised the possibility that early star formation was more efficient, that dark matter halos collapsed faster, or that feedback mechanisms behaved differently under primordial conditions. Alternatively, it suggested that our understanding of how to interpret ancient light might be incomplete, that the signals we read as maturity could be misleading in ways not yet understood. Each of these possibilities carried profound consequences, because they would require revisions not just to galaxy formation models, but to the broader story of how the universe evolved from simplicity to complexity. The presence of this galaxy also highlighted the power and danger of looking too deeply, too quickly, because the deeper we peer into the past, the more we risk encountering realities that do not align with our expectations. The universe, after all, does not care about coherence or narrative elegance, and it is entirely capable of revealing truths that feel inconvenient or destabilizing. This galaxy became a focal point, not because it alone rewrote cosmic history, but because it embodied the tension between what we believed and what we observed. It stood as a reminder that every scientific framework is provisional, built on the best available evidence, but always subject to revision when new light arrives. As discussions intensified, the question shifted from whether this galaxy was real to what its reality implied. Because if it truly existed in the early universe, then it was not just an anomaly, but a signal that something fundamental was missing from our understanding. This realization marked a turning point, because it transformed isolated curiosity into a broader reckoning with cosmic timelines, setting the stage for the next chapter, where scientists would begin grappling with the full implications of a universe that appeared to have grown up far faster than anyone had imagined. Once the reality of the galaxy's existence could no longer be easily dismissed, the implications began to spread outward like ripples across a still surface, touching nearly every assumption embedded in modern cosmology and forcing scientists to confront a question that felt both technical and deeply unsettling, which was not simply how this galaxy formed, but whether the timeline we use to describe the universe's growth was fundamentally flawed. The cosmic timeline is not a casual estimate, but a carefully constructed sequence built from the expansion rate of the universe, the behavior of dark matter, the physics of gas cooling, and the observed distribution of galaxies across space and time. Every piece reinforces the others, forming a delicate balance that allows scientists to reconstruct the universe's history with apparent precision. When a galaxy appears far earlier than expected, it is not merely an outlier, but a stress test applied to the entire structure, revealing which assumptions can bend and which may break. The earliest stages of galaxy formation were thought to be governed by scarcity, because while matter existed, it was spread thin by rapid expansion, and gravity needed time to overcome that separation. Dark matter halos were expected to form first, slowly deepening their gravitational wells before gas could fall in and ignite star formation. This process was believed to be inherently limited by the initial density fluctuations left over from the Big Bang, setting a natural pace for structure formation that could not be easily exceeded. The existence of a massive, organized galaxy at such an early epoch suggests either that these density fluctuations were far more effective than expected, or that gravity operated under conditions that allowed it to act more decisively. If dark matter clumped faster than models predict, then the scaffolding for galaxies could have assembled earlier, providing the foundation needed for rapid star formation. This possibility forces scientists to revisit assumptions about dark matter's behavior, including how it interacts with itself and with ordinary matter. questions that reach beyond astronomy and into fundamental physics. Alternatively, the issue may lie not with dark matter, but with the efficiency of star formation in the early universe. Stars form when gas cools and collapses, but cooling requires mechanisms to shed energy, and in the early universe, those mechanisms were thought to be limited. The first stars were expected to flood their surroundings with radiation, heating nearby gas and suppressing further collapse, creating a self-regulating process that slowed growth. If, instead, early star formation was less disruptive, or if cooling pathways were more effective than assumed, galaxies could have grown rapidly without tearing themselves apart. This would imply that the earliest cosmic environments were not as hostile to structure as previously believed, and that the universe may have been primed for fast assembly rather than gradual evolution. Another implication lies in the way astronomers interpret ancient light itself, because estimating a galaxy's mass and age depends on models of stellar populations that are calibrated using nearby well-understood systems. If the first generations of stars behave differently, producing light that mimics the appearance of maturity, then what we interpret as an old, massive galaxy might be something more exotic. This possibility introduces uncertainty into the very tools used to read the early universe, suggesting that the language we use to translate light into history may need refinement. Yet even this explanation does not fully dissolve the tension, because the galaxy's brightness and structure still demand an extraordinary level of organization at a very early time. As these possibilities were debated, a deeper realization began to take shape, which was that the timeline itself might not be as rigid as once believed. The universe's early phases unfolded under extreme conditions, where small differences in initial parameters could produce dramatically different outcomes. If those parameters allowed structure to emerge faster than our models anticipate, then the neat sequence of cosmic milestones may be more flexible than textbooks suggest. This does not mean the Big Bang is in question, but it does mean that the path from simplicity to complexity may have been far less orderly than imagined. The unsettling aspect of this realization is not that scientists were wrong, but that they may have underestimated how creative the universe can be when operating under unfamiliar conditions. Each adjustment proposed to accommodate the galaxy's existence pulls on another thread, because changing the rate of star formation affects the timing of cosmic reionization, altering how early light reshaped the universe's transparency. Revising dark matter behavior influences the distribution of galaxies at later times, potentially affecting everything from cluster formation to large-scale cosmic structure. The timeline is interconnected, and altering one segment reverberates across the whole. This is why the discovery feels so destabilizing, because it does not offer a simple correction, but demands a re-evaluation of how confidently we believe the universe followed a single, predictable path. The galaxy stands as evidence that the early universe may have been more dynamic, more efficient, and more surprising than the slow, methodical picture we constructed. Yet science does not respond to such challenges with panic, but with careful scrutiny, because before rewriting cosmic history, every alternative must be examined. This is where the story pauses between revelation and resolution, because while the implications are profound, they are not yet conclusions. The galaxy opens a door, but it does not tell us what lies beyond it. To move forward, scientists must confront the explanations that could preserve the timeline, the subtle effects and overlooked processes that might reconcile observation with theory. And so the narrative shifts again, away from what this galaxy implies, and toward the explanations that might contain the damage, setting the stage for the next chapter, where every attempt to explain away the contradiction reveals just how stubborn and unsettling the problem truly is. As the implications of the galaxy's existence rippled outward, scientists turned instinctively toward explanation, not because they wished to preserve old ideas at any cost, but because science advances by exhausting every possibility before accepting that something fundamental must change. The first line of defense was skepticism directed at the data itself, because extraordinary claims demand extraordinary verification, and new instruments often reveal illusions before they reveal truths. Astronomers re-examined redshift measurements with extreme care, because redshift determines how far back in time an object is placed, and even small errors can dramatically alter a galaxy's apparent age. They asked whether the galaxy might be closer than it appeared, masquerading as ancient due to quirks in how its light was stretched and filtered by interstellar dust. Dust, after all, can redden and dim light in ways that mimic extreme distance, and early galaxies were expected to be dusty environments shaped by intense star formation. Detailed modeling explored whether unusual dust compositions could trick Webb's instruments into overestimating age and mass. Yet, as these models grew more sophisticated, they failed to fully resolve the tension, because the galaxy's brightness and structure still required an implausibly rapid buildup of stars. Gravitational lensing was another suspect, because massive objects between Earth and the distant universe can bend and magnify light, making faraway galaxies appear brighter and larger than they truly are. Astronomers mapped the surrounding region carefully, searching for foreground clusters or massive halos that could be acting as cosmic lenses. While lensing can explain some extreme observations, in this case it offered only partial relief, because the degree of magnification required would have left detectable signatures that were not present. Attention then turned to the stars themselves, because the properties of stellar populations play a central role in how astronomers interpret ancient light. The models used to estimate mass and age assume stars form with a particular distribution of masses and lifespans, an assumption based on nearby galaxies where conditions are well understood. But the early universe was not nearby, and its conditions were unlike anything observed today. If the first generations of stars were more massive, more luminous, or more efficient at producing light than expected, then a galaxy could appear older and heavier than it truly was. This possibility prompted intense investigation into population 3 stars and exotic stellar populations that might shine brightly without requiring as much mass or time. Some models suggested that an early burst of massive stars could produce a temporary illusion of maturity, flooding a young galaxy with light that mimicked the glow of an older system. Yet these scenarios struggled to explain the observed organization of the galaxy, because structure implies not just brightness, but stability over time. A galaxy dominated by short-lived massive stars should appear chaotic and transient, not coherent and settled. Another avenue explored involved the physics of gas cooling and feedback, because if early gas cooled more efficiently or resisted disruption from stellar radiation, star formation could proceed at a furious pace. This would require revisiting assumptions about how radiation interacts with primordial gas, and whether early environments allowed energy to escape rather than accumulate. While some refinements improved the situation, they often introduced new problems elsewhere, such as producing too many stars too early, or conflicting with observations of later cosmic epochs. Each attempted fix seemed to trade one inconsistency for another, like pressing down on a bulge in a balloon only to see it pop out somewhere else. As explanations multiplied, a deeper frustration emerged, because none of them fully restored the comfort of the original timeline. The galaxy remained stubbornly inconvenient, resisting efforts to be neatly categorized or dismissed. This is the moment in scientific inquiry where tension becomes productive, because the failure of easy explanations signals that the problem is real rather than illusory. Yet it is also the moment where uncertainty is greatest, because the path forward is no longer clear. Scientists began to acknowledge openly that while individual adjustments could reduce the discrepancy, no single explanation resolved it completely. The possibility loomed that multiple factors were at play, each contributing partially. But even this patchwork solution hinted at a deeper issue, which was that the early universe might have been operating under rules we do not yet fully grasp. The discomfort was not just technical, but conceptual, because it challenged the idea that the universe's early history could be neatly reconstructed from present-day observations using familiar physics. As discussions continued, a subtle shift occurred in how the problem was framed, moving from attempts to explain away the galaxy to efforts to understand what it might be telling us. Instead of asking how to make the galaxy fit the timeline, scientists began asking what the timeline itself might be missing. This shift did not abandon rigor, but it did open the door to more radical possibilities, such as new behaviors of dark matter, altered initial conditions in the early universe, or unknown processes that accelerated structure formation. These ideas were treated cautiously, not as conclusions, but as reminders that cosmology is an evolving narrative, rather than a finished script. The galaxy had done something remarkable, which was to expose the limits of our current explanations without yet offering a clear alternative. It forced scientists to sit with uncertainty, to accept that the universe had revealed a fact before providing the theory to explain it. This uneasy pause, suspended between explanation and revision, is where science often advances most dramatically. And it is from this pause, from the realization that the old story may no longer be sufficient, that the next chapter emerges. Because once we accept that explanations are failing, we are compelled to confront what this discovery might mean, not just for one galaxy, but for our entire understanding of the universe's past, leading directly into the broader consequences explored in the next chapter. As the weight of evidence settled in, and the failure of simple explanations became increasingly clear, scientists were forced to step back and confront a far more unsettling question, which was not how to fix a broken detail in the cosmic story, but how this discovery reshapes the story of the universe as a whole. The appearance of such an advanced galaxy so early in cosmic history does not merely challenge one model or one assumption, but undermines the sense that the universe unfolded in a slow, orderly progression from simplicity to complexity. Instead, it suggests a universe that may have been capable of rapid organization almost from the very beginning. A universe that did not hesitate or stumble as much as we believed, but moved decisively towards structure and richness. This realization forces a re-evaluation of cosmic infancy, a period long imagined as dim, chaotic, and uneventful, now revealed as potentially vibrant and productive. If galaxies could assemble quickly, then stars may have ignited earlier and in greater numbers than expected, flooding the young universe with light at a pace that reshapes how we think about the cosmic dark ages. The era once described as a long wait for illumination may have been shorter, more active, and more complex, altering timelines for when the universe became transparent and when light could travel freely across space. This has consequences for reionization, the process by which early starlight stripped electrons from hydrogen atoms and transformed the universe from opaque to transparent. A faster buildup of galaxies implies a faster reionization, which in turn affects how radiation propagated and how subsequent generations of galaxies evolved. The ripple effects extend further, touching the chemical history of the cosmos itself, because early star formation produces heavier elements that seed future stars and planets. If those elements appeared earlier, then the building blocks of complexity, including the ingredients necessary for planets, may have been present far sooner than assumed. This does not mean life emerged earlier, but it reframes the conditions under which life might eventually arise, expanding the window of possibility. Beyond these practical consequences lies a deeper philosophical shift, because the discovery challenges the idea that the universe's history can be neatly reconstructed by extrapolating backward from the present. Cosmology often relies on the assumption that the processes we observe nearby operated similarly in the past, scaled by time and environment. But the early universe was an extreme place, governed by densities, temperatures, and energies that no longer exist, and this discovery hints that those extremes may have produced behaviors we have yet to fully understand. It suggests that the early universe was not merely a quieter version of the present, but a qualitatively different regime, where familiar rules produced unfamiliar outcomes. This realization humbles the scientific enterprise, reminding us that our models are not mirrors of reality, but approximations constrained by observation. The galaxy discovered by Webb acts as a messenger from a time when the universe was still experimenting with itself, when the balance between gravity, radiation, and matter may have allowed for rapid bursts of creativity. In this light, the discomfort surrounding the discovery transforms into an opportunity, because it opens new avenues for inquiry rather than closing them. Scientists must now explore whether the early universe favored efficiency, whether feedback mechanisms were gentler, or whether unknown processes accelerated structure formation. Each possibility invites new simulations, new observations, and new theoretical frameworks. The story of the universe becomes less like a linear march and more like a dynamic improvisation, shaped by conditions that could produce surprising results. This shift also changes how we interpret future discoveries, because if the universe surprised us once at great distance, it may do so again. The James Webb Space Telescope has shown that when we extend our reach, we do not simply confirm expectations, we encounter realities that challenge them. This forces a recalibration of confidence, encouraging scientists to approach new data with both rigor and openness. The broader meaning of the discovery lies not in any single conclusion, but in the reminder that the universe is not obligated to unfold in ways that feel comfortable or intuitive. It has its own history, written in light, and our task is to read that history honestly, even when it contradicts our assumptions. The galaxy that appeared too early becomes a symbol of this tension, representing the gap between what we thought we knew and what the universe is willing to show us. As the implications continue to be debated, one thing becomes clear, which is that this discovery marks a transition from confidence to curiosity, from closure to exploration. The universe's story is not finished, and the opening chapters may be far richer than we imagined. And it is precisely this realization, that the universe still holds fundamental surprises about its own beginnings, that leads us into the final chapter, where we must confront what this discovery ultimately means for the future of cosmology and for our ongoing attempt to understand a universe that refuses to be simple. As this story reaches its final chapter, what becomes clear is that the discovery of this ancient galaxy is not an ending at all, but a reopening of questions we believed were already answered, because science does not move forward by preserving comfort, but by surrendering it when reality demands more. The James Webb Space Telescope did not arrive to confirm what we already knew, but to reveal what we could not yet see, and in doing so it reminded us that every cosmic story we tell is provisional, waiting patiently for new light to arrive and test its strength. This galaxy, existing far earlier than expected, and appearing far more mature than allowed, does not invalidate decades of careful work, but it exposes the limits of conclusions built on incomplete access to the past. For a long time we told ourselves a story of gradual cosmic awakening, a universe that took its time learning how to build complexity, because that story matched what our instruments allowed us to observe. Webb has now shown that the early universe may have been far more ambitious, assembling stars and galaxies with a speed that feels almost intentional, as if the cosmos itself was eager to become structured. This does not mean the universe is designed or purposeful, but it does mean that its capacity for organization may be greater than we imagined. The discomfort this creates is not a weakness of science, but its strength, because science grows precisely at the moment when old explanations fail and curiosity must take their place. The galaxy forces us to confront the possibility that our timelines are flexible, that the early universe was governed by efficiencies we have yet to fully understand, and that familiar processes like gravity, cooling, and feedback may behave differently under extreme conditions. It invites us to consider that dark matter may play a more dynamic role in early structure formation, or that the first stars may have ignited in environments far more conducive to rapid growth than our models assumed. It reminds us that the light we see is not just illumination, but evidence, carrying encoded information from epochs where our intuitions no longer apply. In this sense, the galaxy becomes more than an anomaly. It becomes a teacher, revealing that the universe does not owe us simplicity or gradualism. The broader implication is that cosmology itself is entering a new phase, one defined less by confidence and more by exploration. Webb is only beginning its mission, and if one early observation can challenge so much, then future discoveries may reshape our understanding even further. This realization shifts the tone of inquiry from closure to openness, encouraging scientists to build models that can accommodate surprise rather than resist it. It also reframes humanity's relationship with the cosmos, because it reminds us that we are not reading a finished book, but an evolving manuscript whose earliest pages are only now coming into focus. There is a quiet humility in this recognition, an acceptance that the universe is older, faster, and stranger than our stories have allowed. The galaxy that should not exist becomes a symbol of this humility, standing as proof that reality can outpace imagination, and that even our most careful theories are temporary shelters rather than permanent homes. As we continue to look deeper into space, we must also look more carefully at our assumptions, recognizing that every new window into the past carries the risk of revision. This is not a failure of knowledge, but a reminder that knowledge is alive, shaped by what we are able to observe. The universe revealed by Webb feels less predictable and more alive, not in a biological sense, but in its capacity to surprise and challenge. It is a universe that does not unfold politely, but one that demands patience, adaptability, and wonder from those who seek to understand it. In the end, the most profound lesson of this discovery is not about one galaxy or one telescope, but about the nature of discovery itself. We learn not by confirming what we believe, but by listening when the universe tells us something unexpected. The oldest galaxy Webb ever saw breaks what we thought we knew, not to leave us without direction, but to point us toward deeper questions, richer models, and a more honest relationship with the unknown. And as Webb continues to collect light from the farthest reaches of space and time, one truth becomes unavoidable, which is that the universe is still teaching us how little we truly understand, and that the greatest discoveries are not those that complete our stories, but those that force us to begin telling them again.